These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you. Here we should start with the concept of temperature. What would be a good symbol for temperature?
Could be Celsius or Fahrenheit or Kelvin.
Those would be good units, yeah.
Oh, then as far as a symbol, it could be T.
Capital T. Since we use lowercase t for time, we can use capital T for temperature. That's right. We don't use Fahrenheit much in science, and we don't use, well, no, that's not true. Well, anyway, in this chapter, I guess in your chemistry course, you sometimes use Celsius and you sometimes use Kelvin. In this chapter, I think we'll mainly use Celsius, so that's what I'll write down here. Now, the temperature is something that we can measure. We can tell when there's something is hot or cold. If the temperature is going up, what does that mean at the atomic level or the molecular level? When we physically perceive the temperature is going up, what's really happening to the atoms or molecules?
They're breaking farther apart from each other.
Yes, that's right. Or that's pretty much right. It might be better just to say they're moving around faster. When the temperature increases, the molecules are moving around faster. So temperature, what we perceive as temperature, is really a measure of how much the molecules are moving around, even though we can't see that directly with the naked eye. All right, so that's the concept of temperature. And let's see, let's review those units a little bit. We could talk about freezing point. Boiling point. Do you know what the freezing point of water is in Celsius?
It's 0 degrees Celsius.
And the boiling point?
100.
So Celsius was purposely, these points were purposely chosen in Celsius to make it easy to work with. So what's the difference in Celsius between the freezing and the boiling point of water?
100 degrees.
Celsius. Now, do you know what the freezing point of water is in Kelvin?
It's 273.15.
That's right. I think you'll probably be usually fine if you just say 273. But that's right. So it's 273 degrees Kelvin. So what's the boiling point of water in Kelvin?
373.
That's true. So what's the difference in Kelvin between the boiling point and the freezing point?
100 Kelvin.
So, if you have a formula that involves the level of temperature, should we use Celsius or should we use Kelvin, or does it not matter?
It doesn't matter.
Now, actually, if the formula involves the level of temperature, it does matter. Because, for example, if you were going to plug in, say, the freezing point, you would plug in 0 in Celsius and 273 in Kelvin. So it makes a big difference. The level of the temperature is much different in Celsius and Kelvin. This would be the level of the freezing point in Celsius, and this is the level of the freezing point in Kelvin. It actually makes a big difference. Which do you think we're supposed to use, Celsius or Kelvin?
Then I guess we would use Celsius.
Actually, in science, whenever a formula involves the level of temperature, you almost always use Kelvin, not Celsius. So that's an important thing to have in our notes. For the level of temperature, you need to use Kelvin. Now, what about if you're focusing not on the level of temperature, but the change in temperature? We could symbolize that by delta T. If you're focusing on the change in temperature, should you use Kelvin or Celsius, or does it not matter?
I guess it wouldn't matter
How can you see that it doesn't matter from this table?
because they're both on the same scale.
That's right. What do you mean by that? How can we see directly that it doesn't matter? Which of these columns here shows the change in temperature?
The difference.
Right, and you can see it doesn't matter. If we imagine raising something from water from its freezing point to the boiling point, the change in temperature would be the same in either scale. It would be 100 degrees in either scale, so it doesn't matter if you use Celsius or Kelvin. For delta T, delta T is the same. In degrees Celsius or degrees Kelvin, so it doesn't matter which you use. So if you have a formula that involves delta T, you never have to do a unit conversion for temperature. You can just use either Celsius or Kelvin. If you have a formula that involves the level of temperature, T, then you have to always use Kelvin. You can't use Celsius. So that's an important idea for chemistry. Now, for this chapter that we're working on right now, we're going to be focusing on changes in temperature. So should we use Celsius or Kelvin?
Either one.
Yeah, either one, it doesn't matter. So for this particular chapter, it's not going to matter whether we use Celsius or Kelvin because we're focusing on changes in temperature. But for other chapters in the chemistry course, it will matter. Okay, so that's the units here. Usually I think it'll be better in this chapter to think in terms of Celsius. Now the next concept we have to think about is heat. Now, heat is a word that you might think that we understand, but it has a technical definition. Heat is energy that's transferred from a high temperature to a low temperature substance. Heat is energy that's transferred from a high to a low energy substance. For example, let's say we have two materials. One is at 30 degrees Celsius and one is at 10 degrees Celsius. If we have these two substances that are in contact with each other, what's going to happen over time?
They both are going to reach a temperature equilibrium.
That's right. So which way will the heat flow?
From left to right.
Like this?
Yeah.
Yeah, that's right. Heat is going to flow in this direction. Until, when will the heat stop flowing? The heat will stop flowing when the two sides have the same temperature. Now, that doesn't necessarily have to be smack dab in the middle at 20 degrees. It depends on the nature of the substances. So eventually, they're going to end up at the same temperature. We can't predict yet what that temperature might be. It might be, for example, it might be that this just falls to 25 degrees Celsius. If this falls to 25 degrees Celsius, this is going to end up at 25 degrees Celsius too when we get to equilibrium. We can't tell exactly what this temperature will be from the information I gave you. Do you happen to know what a common symbol is for heat?
Q.
Yes, good, that's right. Doesn't seem very logical, but we use Q for the heat that's transferred. All right, good. And what do you think will be the unit for heat?
Kilojoules.
Yeah, that's a reasonable answer. What would be the SI unit for heat?
Joules.
Yeah. And I think that's what's going to be more common in your class, to use joules. But actually, both of those could come up, so let's write both of them. I think it'll be more convenient for us to work in joules, but I think you'll definitely see some problems with kilojoules too. Can you think of any other units for heat that you might have seen in this chapter?
Maybe a calorie.
Yeah, that's a good answer. That's right. So another unit for heat is calories. Actually, I don't know if your instructor really is testing that too much, though. I didn't see that in the sample problems you sent me. So that's in your textbook, but maybe we won't get into that. But another unit for heat would be calories. We'll see if we need that. Now, one big mistake that people make here is I think that in ordinary English, people tend to use temperature and heat as synonyms sometimes. But in chemistry, they don't mean the same thing. So one thing we really want to make clear is heat is not the same thing as temperature. After all, what are the units for temperature? What are
I'm sorry, say that again?
What are the units for temperature?
Units for temperature are degrees Celsius and Kelvin.
Yeah, but what are the units for heat?
Could you repeat that?
What are the units for heat?
Units for heat are joules and kilojoules.
So you can see they're not the same thing. This little picture here shows the relationship. Remember that heat is energy that's transferred from a high to a low temperature substance. So that tells us the relationship. I'll put a Q here to show that here's the heat that's being transferred. But heat and temperature are not the same thing. All right? Now we need to talk about an important graph that's called the heating curve. This is used for solving problems in this chapter. All right, and we'll do the heating curve for water. Every substance has its own heating curve, but water is the most important. And in this curve, on the axes, we have heat on the horizontal and temperature on the vertical. I'm going to start here. And let's call this, say, negative 20 degrees Celsius. You don't have to start exactly here, but let's call that negative 20 degrees Celsius. Now, what phase will water be in at negative 20 degrees Celsius?
Negative 20 degrees Celsius, that would be a solid.
Yes, or also called ice. So it would be in the solid or ice phase. Good. Now, what does it mean as we move to the right? Moving to the right here means that we're adding heat. What do you think is going to happen to this ice at negative 20 degrees Celsius if we add a little bit of heat? If we add a little bit of heat to the ice at negative 20 degrees Celsius, how will it change?
Could you repeat that?
If we add a little bit of heat to the ice at negative 20 degrees Celsius, how will the ice change?
It's going to change to liquid.
Now, that would be if we added quite a bit of heat. If we only add a little bit of heat, what will change is that its temperature will rise. As we add heat, the ice will get hotter. That really should just be common sense. But that process will stop when we get to 0 degrees Celsius. So what does this represent? This represents ice at negative 20 degrees. What does this point represent? Well, maybe this is ice at negative 15 degrees Celsius. What does this point represent? Well, maybe this is ice at negative 10 degrees Celsius. And what does this point represent? This point is ice at 0 degrees Celsius. Now let's say we take this ice at 0 degrees Celsius and we add more heat. Say we add a little more heat. What will happen to the ice at 0 degrees Celsius if we add a little more heat? If we have ice at 0 degrees Celsius, how is it going to change if we add a little more heat?
It's going to start becoming liquid.
That's right. And what will be happening to its temperature as it melts?
The temperature will stay constant.
That's a good answer. That's right. While we're melting, the temperature stays constant. So that part of the graph would look like this. So what's the name of the process that's happening here? melting. And there's another name for melting, which is a little weird. It's also called fusion. I'm not sure why, but melting is also called fusion. So what do we have at this point? This point represents now liquid water at 0 degrees Celsius. Now, what would happen if we take this liquid water at 0 degrees Celsius and we add a little more heat?
It'll still be liquid.
True. How will it change?
The temperature will change.
Increase or decrease?
It'll increase.
Yeah, so now the temperature will keep rising, but the temperature is not going to rise indefinitely. Where will the temperature stop rising?
Probably at 100 degrees Celsius.
That's right. Since we're thinking about water. So remember, this point here represents liquid water at 0 degrees Celsius. This would be like liquid water at 20 degrees Celsius. So what does this point represent?
That would be a gas or a water vapor at 100 degrees Celsius.
Now, it actually doesn't represent that. You can see the temperature is 100, but so far we haven't added enough heat to turn it into a gas. We actually haven't added enough heat to turn it into a gas, so this would still be liquid water. It would just be at 100 degrees Celsius. But if we take this liquid water at 100 degrees Celsius, what's going to change if we add a little more heat?
The temperature.
Actually, that's incorrect. Now that we're at 100 degrees Celsius, we can't raise the temperature anymore until we do something else. If we have liquid water at 100 degrees Celsius, how will the water change if you add more heat?
Oh, now it's going to start evolving into a gas.
Yeah, now it's going to start vaporizing. And what's going to happen to the temperature while it's vaporizing?
It's going to stay the same.
That's right. The temperature won't keep increasing. And this graph isn't really going to end up drawn to scale, but it shows you qualitatively what's going on. So that happens here. So what's the name of this process? This could be called vaporization. Or I guess you could also call it evaporation. Maybe vaporization is a better word. Vapori, or boiling, actually. You could also call it here. So what does this point represent? What do we have here? For example, this point was liquid water at 0 degrees Celsius. So what does this represent?
That's gas or water vapor at 100 degrees Celsius.
That's right. Now it's in the gas phase or the vapor phase. Now, if we take this gas phase at 100 degrees Celsius and we add a little more heat, how will it change?
It won't really. I mean, you'll just increase the temperature, but it's a gas, so it'll just evaporate.
Okay. Now, so when you said it won't, I guess what you mean is that the phase won't change anymore. And that's true. The phase is not going to change anymore. But then, as you said later, the temperature will keep increasing. So now we should draw this again to show that the temperature is increasing. Now, it would be incorrect to say that it keeps vaporizing. It was vaporizing over here. Once the whole thing is turned into a gas, there's no more to vaporize. This point, so this point represents when the whole substance is turned into a gas, so no more can vaporize. So this then gives us the heating curve for water. Here we have the heating curve for water. So, for example, let's review that again. This point represents ice at negative 20 degrees Celsius. What does this point represent?
That would be ice at 0 degrees Celsius.
Excellent. How about this point?
That would be liquid water at 0 degrees Celsius.
That's right. With practice, we can just read that right off the graph. Now we're in the liquid phase at 0 degrees Celsius. What does this point represent?
That's is liquid water at 100 degrees Celsius.
That's right. Notice that even though we're at the boiling point, at this point it's still liquid because we've only added enough heat to get to the boiling point, not enough to actually boil. What does this point represent?
Water vapor at 100 degrees Celsius.
That's right. And for example, what would this point represent?
Um, it would just be water vapor at something above 100 degrees Celsius.
Yeah, that's a good answer. Okay, good. So by the way, then what would say this point represent? Well, this would be a point when, say, about a third of the substance has melted. This is when about a half the substance is melted, and this is when all of it is melted. So, for example, what would say this point represent?
That would be maybe like a quarter of the liquid water evolving into vapor.
That's right. And this would be when it's all evolved into vapor. That's why it can't vaporize anymore. Now, we can also go in the opposite direction. We can remove heat. What happens to a gas if you remove enough heat? If you remove enough heat from the water vapor, it'll turn into a liquid. I guess that's how clouds turn into rain. Do you know what the name of this process is when a gas turns into a liquid? That's a word that's not used that much.
Condensation.
That's right. That's a good answer. Condensation. I think sometimes, like when you get out to your car early in the morning and you see a whole bunch of water on it, you might say it's from condensation. The water vapor in the atmosphere is condensed onto the car. So you could also move in this direction, and then you would say this represents the point when about a third of the gas is condensed, and this is when about 2/3 of the gas is condensed, and this is when all of the gas is condensed. We also need a name for this process. What would be a good name for that?
Freezing.
Freezing, yeah. You could just call it freezing or maybe solidification. So those are terms that you're probably expected to know, these 4 terms. Again, fusion means melting. That's kind of a weird term. All right. So we're going to use this graph to solve problems. Let's see. So here's our graph. So one thing to notice here is, remember that heat is energy. Heat is a form of energy. So what happens when you add heat to a substance? This tells us when you add heat to a substance, either the heat will raise its temperature or it'll change the phase, but it never does both simultaneously. First, it's raising the temperature. Then when we get to the freezing point, all the heat goes into changing the phase and it stops raising the temperature. Then you start raising the temperature again, and then when you get to the boiling point, all the heat starts going into changing the phase and you're not changing the temperature anymore. Until the phase change is complete, you're not changing the temperature. So by the way, this is called a temperature change region. This is where the temperature is changing. This would be called a phase change region. So what type of region is this?
That would be a temperature change region.
And how about this?
Phase change region.
And here. Which type of region
That'd
is this?
be temperature change.
That's right. But we never have both at the same time. That really shows you that heat is not the same thing as temperature. Sometimes heat raises the temperature, but sometimes it changes the phase. Okay, good. So, how much heat does it take to raise the temperature of something? Different substances require different amounts of heat to change the temperature. So let's take a look at that table you sent me. So here's the table that I guess you guys are using in your course. So these are what are we called specific heats or specific heat capacities. So what's the specific heat for liquid water?
4.184 joules per gram degree Celsius.
Right. 4.184. If you were going to write that out, you would write it like this. That's not really obvious from this, but notice that the grams and the degrees Celsius are both in the denominator. Like so. How do you think you would interpret this number? What does this number tell us?
For 1 gram of a substance, in this case water, it takes 4.18 joules of energy to raise 1 gram of water 1 degree Celsius.
That was a good answer. That's a very good answer. So maybe we've talked about this trick before. When you have multiple units, a good trick is to stick the number 1 in front of a bunch of the parts. So we know that we could, if we stick these ones here, that's not going to change the number. And now we can interpret this better. So I think your interpretation was very good. You said this means that if we had 1 gram of water, liquid water, it would take 4.18 joules. 4.18 joules of what? Of heat. 4.18 joules of heat to raise the temperature by 1 degree Celsius. Good. That's a good answer. So, for example, how would you interpret this number, this 1.23?
For 1 gram of sodium, it would take 1.23 joules of heat to raise 1 gram of sodium 1 degree Celsius.
Good. So, of all the substances in this table, which is the most difficult to raise the temperature? Which of these is the most difficult?
It would have to be hydrogen gas.
Yeah, because that takes the most heat. So notice when the heat capacity is big, that means it's hard to raise the temperature. What does it mean for these things where the heat capacity is low?
It's easier.
Easy to raise the temperature. It doesn't take much heat. So relatively speaking, is it easy or hard to raise the temperature of liquid water?
Could you repeat that?
Relatively speaking, is it relatively easy or relatively hard to raise the temperature of liquid water?
It's relatively easy.
And why did you say that?
Well, it's relatively easy compared to hydrogen gas.
I guess, so compared to most substances, is it easier or harder to raise the temperature of liquid water than for most substances?
Then in that case, it's relatively hard because most other substances on this table require less energy.
Yeah, that's right. Now, it's true that this is still a lot smaller number than the number for hydrogen gas. But you know, hydrogen gas and helium gas are kind of rare substances. We don't encounter them very much in ordinary life. If you take out those two rare substances, notice that water is the most difficult to raise the temperature. Of all these ordinary substances, water is the most difficult to raise the temperature. That's an interesting fact about water. It's very hard to raise its temperature. It resists changes in temperature. That has a bunch of important implications. Okay, now, so going back to water here, what if you didn't have 1 gram? And what if you didn't want to, so let's say that you wanted to raise 2 grams of water by 1 degree Celsius. How would you figure out how much heat that takes?
Just multiply 4.184 by 2.
So if you wanted to raise 2 grams by 1 degree Celsius, you would just do this calculation, and it would come out to be approximately 8 joules. Notice that the units here would cancel. Suppose that you wanted to raise 2 grams of water by 3 degrees Celsius. What calculation would you do to figure out how much heat that would take?
2 grams of water by 3 degrees Celsius, then you would take 4.184 joules per 1 gram per 1 degree Celsius, and then multiply that by 2 grams, and then also multiply that by 3 degrees Celsius, so all the units cancel.
That's right. And what units would you end up with?
Just joules.
And that would be approximately 6 times 4, so that would be approximately 24 joules, rounding off. Okay, so now we can get a formula. What's the name of this number? What concept is this?
Heat.
No.
Oh, I'm sorry. That is a joules, which is a unit of heat.
What I meant was this whole thing.
Oh, that's the specific heat
Yeah,
of
this
water.
is the specific heat. I haven't mentioned it yet, but the symbol for specific heat is C. I should have mentioned that before. So actually, your textbook I thought used S, which I haven't seen before, but I have an old edition. Oh, I noticed in the practice problems you sent me, there was a couple. There was some writing in those. Is that your writing?
Yeah.
Okay, so I can see you're using C. So I guess your professor is using C for specific heat. So we'll keep using C. And what does this concept represent? What's the name of the concept we would measure here?
Mass.
Yeah, what would be a good symbol for that?
M.
Good. And what concept are we measuring here?
Temperature.
Are we measuring the level of the temperature or the change in the temperature?
The change.
Yeah, because remember we said this is how much heat it takes to change the temperature by 3 degrees Celsius. So what would be a good symbol for the change in the temperature?
Delta T.
Right, not T, but delta T. So here's an important formula. Formula is usually written like this. But notice that the formula should be obvious from the units for specific heat. We were able to figure out this from the units for specific heat, but it's still probably worth memorizing this formula to make the problems easier. So the point is, the way to figure out the heat is to work through this. Okay, good. So that gives us that formula. So I should have been more careful and introduced this idea of specific heat. What did we say is the symbol for specific heat?
C.
Lowercase c. We want to use a lowercase c for specific heat. I can see from your work that that's what you're using in your course. And we've just learned what are the units for specific heat. What would be the units for specific heat?
It would be joules per gram degree Celsius.
Joules per gram per degree Celsius. We were just learning that. Good. One thing that's confusing, though, is you can see from that table we were looking at a second ago. Whoa, that's not what I wanted. You can see from this table that there's another name for this. Here they didn't call it the specific heat, they called it the specific heat capacity. So those two things mean the same thing. So we need to add that. This is also called the specific heat capacity. Those two mean the same thing. Okay, and this tells us how hard it is to change the temperature of a substance. And then we have this formula. How would you calculate delta T? What would be a formula for calculating delta T?
Final minus initial.
That's right. Maybe that's a better way to write this because that's what you're going to use for solving problems. So maybe it would be better to just write it like this. By the way, a lot of people that are taking these chemistry courses, they're oftentimes pre-med students. And so sometimes the instructors use a memory aid here because the admissions test for medical school is the MCAT, and this kind of looks like MCAT. So I don't know if you're pre-med, but anyway, that can be a useful memory aid. This looks like Q equals MCAT. So that can just be a memory aid for this formula. Like I said, the formula should be obvious from the units, but anyway, it's good to just memorize the formula. All right, I think this version of the formula here is probably the easiest to use. Now, what units should we plug in for temperature here? Kelvin or Celsius?
It wouldn't matter.
That's right. It doesn't matter because what we're really thinking about is the change in temperature. So notice we could just as well have said this was joules per grams per Kelvin. We could have said per Kelvin here because we're talking about just the change in temperature. Okay, good. So let's see how we would use this for some problems. So what was the specific heat then for liquid water?
4.184 joules per gram degree Celsius.
Good. What is the specific heat for water, solid water? What's the specific heat for solid water?
2.010 degrees or joules per gram degree Celsius.
That's good. You found that over here. That's the specific heat for solid water. And what's the specific heat for water vapor?
The same.
The same as for ice. But notice that those numbers are not the same as for liquid water. So this is something you have to watch out for. The specific heat can be different if you change phase. That's something to watch out for when you're solving problems. You can't just say, oh, I need water. You need to get water in the right phase. Here we have liquid water, here we have ice, and here we have steam. So that's one thing to watch out for when you're using this table. It's kind of weird that they didn't put them next to each other in the table, but anyway, those are all numbers that you might need. All right. Let's see. Okay, so let me talk you through what is a good systematic way to do a problem like this. Do you have this copied down?
Yeah.
All right, so let's work through this together. So first of all, it's always good, we've talked about, to write down a symbol for what the question's asking us. What would be a good symbol for what this question's asking?
Q.
That's right. Also, it's always good to try to get a prediction. So one thing we can predict here is, in this case, is heat going to be released or absorbed?
It's going to be released. I'm sorry, no, it's going to be absorbed. Oh, wait a minute. From 30 degrees.
Is the water going to be absorbing heat, or is the water going to be releasing heat?
The water is going to be absorbing heat.
I think that's a mistake, because it's getting cooled down, right? If its temperature is lowering, doesn't it have to lose heat?
Oh, yeah, so it would lose heat.
So the water is releasing heat. So that means we would predict that Q will be negative for the water. When something is releasing heat, it ends up having a negative Q. And when it's absorbing heat, it has a positive Q. I should have said that explicitly before, but we're saying it now. Something that's releasing heat, this is losing heat, so we can predict that Q will be negative even before we do calculations. It's always good to predict before you start. Well, now let me show you how to work through this systematically. I think it's really important on these problems to use a heating curve, at least until the problems get really easy for you. So we're going to try to use a heating curve on each problem. That will help us to organize our work as the problems get harder and harder. So we need to label the initial and final points on this curve. Where is the initial point? Where are we starting initially?
We're initially starting at 20 degrees Celsius.
I don't think so.
I'm sorry, 30 degrees Celsius.
Yeah, because remember we're cooling from 30, and what phase are we in?
10 grams of water, so we're in the liquid phase.
Yeah, we know we're in the liquid phase, so I'm not going to do this to scale, but I'll just say, suppose that this point here not to scale, is 30 degrees Celsius. And we'll label that as the initial point. And then what's our final point?
20 degrees Celsius.
Which I'll label down here. And we should see to ourselves that we're moving in this direction. And you can already see that Q is going to be negative because we're moving to the left. So now what's the equation we need to use? We need to use this formula. Or maybe it's better to always just write it like this to avoid confusion. What should I plug in for M?
10 grams.
And for C?
4.184 joules per gram degree Celsius.
That's from the table that we were looking at before. And for T final?
It would be 20 minus 30, which is negative 10.
That's right. So go ahead and take out your calculator and do this calculation and see what you get.
I got negative 418.4 joules.
Good. Usually I don't put in units when I'm working with equations, but here I think you can learn from putting in the units. You can see how the units cancel, degrees Celsius cancel. And it's good that you saw the answer came out negative, because 20 minus 30 is negative 10. And that negative answer matches our earlier work, right? We were predicting that this was going to be negative. It's releasing heat because it's cooling down. Okay, so that's our first example. So the answer here would be negative 418.4 joules. So this is the method for these problems. So one thing you should always try to do is always make a heating curve and label the initial and the final points. This problem might not have seemed very complicated, but the problems get more and more complicated. And the more complicated it gets, the more helpful it is to show it on the heating curve. So we should do that with each example. All right, good. Okay, well let's try this problem. So this time you can try the problem. So talk me through what you would be writing down to solve this problem.
Well, on the heat curve, we see that the temperature increased from negative 15 degrees C, which is the initial, to negative 10, which is the final. So that means, and we want to look for Q because that's what the question is asking for.
Good.
So that means Q is equal to MC
Good.
delta T.
So where would our points be? We're starting at negative 15 in which phase?
The solid phase.
Right, so we'd go from here to here. It's good to actually label those points from negative 15 to -10. And let's get a prediction. What can you predict about Q?
It should be positive because it's gaining heat.
You can see it's positive because we're moving to the right. Okay, that's good. So what would you write down next?
So then in our equation Q equals mc delta T, we can substitute 20 grams for M, 2.01 for water, joules per gram degrees Celsius. And then delta T, which in this case is final -10 minus initial -15.
I'm sorry, yeah, so what do you write for the temperature?
5.
Positive or negative?
Positive.
That's right. So it would be -10 minus 15, which comes
Yeah.
out to be +5. Okay, so let's keep going.
And then just multiply it. 20 times 5 is 100 times 2.01, and that's equal to 201 joules.
Positive or negative?
Positive.
Yeah, notice that if you do things correctly, the formula will automatically tell you whether it came out positive or negative, although we should have been able to predict that anyway. So ice. Yeah, so it looks like so you remembered here you had to change to a different specific heat. Now we need the ice, which is 2.01. So it looks like we did that correctly. Good. Now, by the way, notice that technically this is the specific heat of ice at 0 degrees Celsius. But we'll just have to use that for the ice at any temperature because that's the only number we have. So we'll just have to approximate and say this is the specific heat for ice anywhere. That'll be a good enough approximation for this course. Okay, good. All right. Let's see. Here's a new problem. Talk me through what you would write down for this problem.
Ten joules of heat is removed from 2 grams of liquid water at 70 degrees Celsius. What is the new temperature? Well, we know that the initial temperature is at 70 degrees Celsius and it's in liquid water. And they're looking for the new temperature, so I guess they're looking for TF.
That's good. It's good to write down a symbol for the question.
So we can use Q equals mc delta T.
That's good. Let me interrupt you for a second. What could you predict here?
If heat is removed, that means it's being released. So that means that the final temperature would have to be a smaller number,
Smaller than what?
smaller than 70 degrees.
That's right. And let's also build that into the picture. So what do we know about our final point? Is the final point to the left or the right of the original point?
It'll be to the left.
So I should put that into the picture. Here's the final point, and we could even mention this is the question, and this point is the one we know. So it's always good to build these into the picture. Okay, but you're right. This is the correct equation. So now what?
So now we can substitute 10 joules for Q, and that is equal to 2 grams times the liquid water, which is 4.184 joules per gram degrees Celsius. And then delta T would be TF minus 70 degrees C.
Good.
Now what we can do is we can add 70 degrees to both sides. Actually, well, I know that the grams will cancel once we multiply.
One thing that'll make this
See,
simpler
if we take
is
2 grams, we multiply it by 4.184.
one thing I'll suggest is now that the algebra is getting more complicated, don't try plugging in the units. We know we don't actually have to write down the units. Since our units are all consistent, we know they're all going to cancel out. So the algebra will be clearer to you if you just write down numbers like this without trying to deal with the units as well. So how would you solve this equation?
Well then, first I would add 70 degrees to both sides, and then I would multiply
So
2 times
let's do that step by
4.184,
step.
which gives me.
So let's do those step by step. So what do you get after the first step?
So after adding 70 degrees to both sides, you'll get 80.
On the left side. Now there's actually an algebra mistake there. We can't actually add the 70 yet because it's stuck inside this parenthesis. As long as the 70 is stuck inside this parenthesis, you can't really add it to both sides. Or you could, but it won't make the equation cancel. Before we can do anything else, we need to simplify this right-hand side. How can we get rid of these parentheses? How can we simplify the right-hand side and get rid of the parentheses on the right-hand side?
You could multiply 2 times 4.184, which gives us 8.368, and then distribute that.
Yes, we have to use the distributive law. So what would be the new equation you get when you use the distributive law?
So then 10 is equal to 8.368 times TF minus 70. Then we distribute that 8.368 times 70 is equal to so now 10 is equal to 8.368 TF minus 8.368 times negative 70, which is equal to negative 585.76. Now we can add 585.76 to both sides. And now we'll have 595.76 is equal to 8.368 TF. and then divide both sides by 8.368. And then TF is equal to 71.2 degrees Celsius.
Okay. Whoa. Did we screw up? Oh, yeah. I'm sorry. We messed up. I should have caught our mistake. All right. Let's go back. Because that doesn't match our prediction, does it?
No, it doesn't.
All right. Well, it's a good thing we made that prediction. All right. So, is this substance absorbing or releasing heat?
It's releasing heat.
So, should Q be positive or negative? Should Q be positive or negative when you're losing heat?
Oh no, it's gaining heat because Q is positive.
Well, that's a number that you wrote down. That wasn't what you were given. So we need to figure out what Q is. So are we really absorbing heat? Is the water actually absorbing heat or releasing heat based on the problem?
Based on the problem, it's gaining heat
Why did you say that?
because its initial is at 70 degrees, but after the problem, after all the math, the new one is the new temperature is 71.2. So
Yeah, I'm sorry.
that
I
means that
confused you by not finding our mistake. This is what we figured out, but we might have made a mistake. This is not what I mean based on the problem is I mean based on this. Based on the information you were given originally. Based on the information we were given originally, are we gaining or losing heat?
so 10 grams or 10 joules of heat is removed. That means that it is being released. So that means that it's negative.
Yeah, so we shouldn't have said Q was positive 10. We should have said Q was negative 10. I should have caught that mistake sooner. So that's something I should have warned you about. When you're plugging in Q, you have to be careful in this equation to plug it in the right way. So here we should be plugging in negative 10 for Q. So that'll change some of our math here. So I guess this number 595 is wrong. So let's do that step again.
So instead, it would actually be 575.
That's right. So now what's our new answer?
.8 degrees Celsius.
That's right. We know the prediction is right. We know that if heat is being removed, the temperature has to fall. So that our earlier answer didn't make any sense. That's a good example of why it's good to make a prediction to catch your mistakes. I made a mistake there. Okay, notice that the temperature didn't change very much. That's not too surprising because remember it's not very easy to change the temperature of water and we weren't removing that much heat. Okay, so this is a harder example than we had before. So let's see, what are the things that we learned from this? One thing we learned, the big thing is when you're plugging in Q, you have to decide whether Q is positive or negative. They said 10 joules, but you have to decide if that's translated into positive 10 or negative 10. That was the biggest lesson. Another lesson is that when the algebra gets harder here, don't bother plugging in the units. As long as our units are consistent, we don't need to plug them in this way the math is easier. And then I think we had some algebra problems here. At first, I think you thought that you could cancel this 70 by just adding 70 to both sides. Now you can see why that's wrong because there isn't really a 70 on the right. There isn't really a 70. There's a 585.76. Once you actually do the distributive law, you can see there really isn't a 70 here. It's 585.76. So as long as the 70 is inside the parentheses, you can't get rid of it by canceling. So the key is to get rid of the parentheses first by using the distributive law. So we have to be careful with that algebra. All right, so that would be a good example to go back and try again. That was a little bit more challenging than the ones we did before. Okay, let's try this problem.
Okay, well, 15 grams of heat is added to water, steam at 105, find the new temperature. So they're asking for the final temperature. And we know that the initial temperature is 105 degrees C, and since 15 grams of heat is added, that means it's gaining heat, which means that it'll be negative Q. So that would mean that we can say negative Q is equal to MC
Now,
delta
let's get a
T.
prediction. What would you predict here?
We would predict that the temperature will increase since it's gaining heat.
So the temperature will end up being bigger than what?
It'll be greater than 105.
Okay. So should I put the final point here to the right or to the left of the initial point?
To the right.
Okay. All right, and then what?
$15 grams of heat is added to water.
That didn't make much sense, did it? Let me try again. It looks like the problem didn't make sense. Let's try this. I didn't write this problem very carefully. 15 joules of heat is added to 3 grams of steam. The problem wasn't written very well. All right. So let's try this. No, I'm still got it wrong. 15 joules. I meant to say 15 joules.
Q is equal to MC delta T. And since it's adding heat and it's gaining, that means that Q will be positive. So positive 15 is equal to 3 times the specific heat of steam, which is 2.01 times TF minus 5. And then 15 is equal to 6.003 times TF minus 105. Use the distributive law. And 15 is equal to 6.03 TF minus 633.15. Add 63.15. So 63.15 plus 15 is equal to 648.55 is equal to 6.003 TF. Divided by 6.03 divided by 6.033. And then RTF is equal to 107.55 degrees Celsius.
Good. Okay, good, which matches our prediction. So in this problem, what was Q?
Q was 15 joules.
Positive or negative?
It was positive.
How did you know?
I'm sorry.
How did you know that Q would be positive?
I don't know because since it's being added it's going to gain heat, which means that it's going to be positive because the temperature is going to increase.
Yeah, or just because it's getting heat. When you were first talking about the problem, at first it sounded like you were saying Q was going to be negative. You might have misread it. I didn't write the problem very well at the start, so that might have been confusing you. But anyway, you ended up with the right answer. Since heat is being added, Q is going to be positive. Okay, good. So that's some good progress on that. So now we know how to figure out how much heat it takes to change the temperature, or how much the temperature will change when we add heat. But you can see from the graph there's something we haven't talked about yet. We haven't talked about how much heat it takes to change the phase. We haven't talked about the phase changes yet. All right, hopefully this is the table that your instructor is going to use. This is probably the best one for this course. So using this number here, what does this number tell us? Do you think? This was the heat of fusion for water. How do you think you would interpret this in words? What does this tell us?
So it takes 334 joules to melt 1 gram of water.
That was good. Good. That's a good answer. So you used the trick we talked about of putting a number here on the bottom. We won't change anything if we put in the number 1. And then I think you interpreted this very well. This tells us that it takes 334 joules of heat to melt 1 gram of water. You remembered that fusion means melting. Would you need to add 334 joules or release 334 joules to melt the water?
We'd have to add it.
That's right. So, by the way, how much heat do you think would be released if we freeze 1 gram of water? If we freeze...
Probably the same 334.
Okay, that's good. That's right. That's the right answer. So notice, what's the heat of fusion of water? 334. So what do you think would be the heat of freezing of water?
It would be negative 334
Right.
joules.
Basically, numerically, it's the same thing. It's the same number here. So that's why they didn't include freezing. All they need to tell you is fusion. And then how about heat of vaporization for water? That is 2260. So how would you interpret this number?
That's to get liquid water to vaporize. So for 1 gram of liquid water, it would take 2,260 joules to vaporize it.
Okay, good. That's right. Now, and how much heat do you think, would you have to add that heat to vaporize it or release that heat?
I'm sorry?
If you wanted to vaporize water, would you need to add the 2260 joules or release the 2260 joules?
You want to add it.
Yeah. How much heat do you think it would be released if you condensed 1 gram of liquid water, 1 gram of water gas? How much heat is released if you condense a gram of water steam?
2,260 joules.
That's right. So notice that the heat of vaporization also tells you about the heat of condensation. That's why we only need 2 constants here. Now notice that this table here is a little bit mixed because some of the things here are solids. Notice that actually it would be kind of weird to vaporize aluminum, right? Notice that this is a very big number here. That's not surprising because, you know, it would take, you don't every day see aluminum or gold or silver being vaporized. So these numbers wouldn't come up very much. Ethanol and butane, however, those are things that would be much easier to put into gas form, and obviously water. So of these 3 substances on the bottom, which of these 3 substances on the bottom is hardest to vaporize?
Water.
Yeah, it's not even close, right? this is similar to what we said before. Remember, we saw that water has a high specific heat. You can see that here too. It's really hard to change the temperature of water, and you can see it's also hard to vaporize water. Of course, these numbers are even higher, but these are almost of not very much practical importance because these are substances that almost never vaporize in real life. Of substances that you commonly vaporize in real life, water is quite difficult to vaporize. So it's hard to change the temperature of water or to vaporize the water. Those are some things that are good to know about water. So these are called the heat of fusion and heat of vaporization. I guess this table also includes the specific heats as well. So that's the numbers that you might already have seen. So how much heat would it take to melt a gram of water? How much heat would it take to melt a gram of water?
How much heat would it take to melt a gram of water? $334 joules.
That's right. You would just use this idea here. How much heat do you think it would take? How would you calculate how much heat it takes to melt 2 grams of water?
Could you repeat that?
How would you calculate how much heat it would take to melt 2 grams of water?
Just take 334 and multiply it by 2.
That's right. How would you calculate how much heat it takes to melt 3 grams of water?
334 times 3.
That should be obvious from common sense. But you can also see that it's obvious from the units. If you did that calculation, the grams would cancel, and you would end up with joules. So let's see, what would that come out to be? 4 times 3, that would come out to be 1,000, approximately 1,000 joules. So we can get a formula here. What concept does this represent? What concept does this number represent?
It's Q.
That's right. And what concept does this represent? The 3 grams.
That would be the mass.
And what concept does this represent?
That would be the heat of fusion for water.
That's right. What would be a good symbol for that? That's not very standardized. That handout we were looking at uses delta H for that, but I don't think that's the best symbol for solving problems. I'm going to use L for that. I think that stands for latent heat. Anyway, L is a good symbol for heat of vaporization or heat of fusion. So here's our formula. Q equals mL. And L is just either the heat of vaporization or the heat of fusion. Different books use different symbols for that. Now, one thing to keep in mind here is remember that when we used the Q equals mc delta T formula, it kind of gave us the right sign automatically. If we plugged in the right sign, if we did final minus initial, this gave us the right sign automatically. This equation isn't going to do that. Here we have to figure out the sign ourselves. So to remind ourselves of that, I'm going to put a plus or minus sign here. So the purpose of this plus or minus sign is to remind you that it's our job to figure out whether this is going to be positive or negative. You can't just assume this is positive. That's a common student mistake. You have to decide whether it's positive or negative. This one, you don't have to decide ahead of time if it's positive or negative. If you do the math right, it'll come out right automatically. So we don't put a positive or minus sign here. For example, let's say that we are melting something. If we're melting something, should we use a plus or a minus sign here?
It should be, if it's melting, then it should be a plus sign.
How about if you're condensing?
Minus.
Good. How about if you're freezing?
Minus.
Because you need to lose heat to freeze. How about if you're vaporizing?
Plus.
Because you need to add heat to vaporize something. So if you're vaporizing or melting, this you would use a plus and you would use a minus for these. Here, you don't have to figure out the sign ahead of time because the math works it out for you. So this is important. People tend to get the signs wrong when they're solving problems, so we have to watch out for that. Okay, good. Okay, talk me through how you would do this problem.
Okay, 10 grams of liquid water at 0 degrees C changes to solid water at 0 degrees C. Find the heat transfer to the water. Well, our final and our initial and final temperature are the same, and they're looking for the heat transfer, so that would still be Q.
That's good.
But since we have a mass and the temperatures are both the same, and since we have a phase change from liquid to solid water, that means that we have to remove heat. So that means that Q is equal to negative mL, where L is the latent heat, and that means Q is equal to negative 10 grams times the latent heat, which is, let's see, since it's going from liquid to solid, that's freezing, and that freezing temperature of water is 334 joules. So 334, and that means that Q is equal to negative 3,300 3,340 joules.
Okay, that seems like a good process. One thing I want to do is use the heating curve still. Where should I put the initial point here?
Initially, it would be at 0 degrees in the liquid phase.
Here? Is this the right point for the?
Yes.
Is this the initial point?
Yeah.
Sorry, that was a little bit of a trick question. This is not the initial point because this is 0 degrees in the solid phase.
Oh, yeah. It would have to be to the dot right next to it on the right.
Yeah, so it's important for us to get comfortable with this. This graph will be very important as the problems get harder. So where's the final point?
Since it's a solid, then it would be the one to the left.
This point here. Okay, so it would be good to put this, and you can see again from the graph, we're moving to the left, so Q is decreasing. So the important thing here is that you remember that Q had to be negative. That doesn't come from the formula. You had to figure that out yourself. We could have predicted that from the start here. Okay, so that seemed like that was a good process. Even though we're freezing and not fusing, you knew to use the same latent heat. So that was a good process for that. Okay, so that's the method for that problem. Good. So let's say that we're moving in this portion of the graph. What's the equation for analyzing this portion of the graph? What's the equation we use to
That
analyze
is
this
the
portion?
temperature change region.
Yeah, so what's the equation that we use to analyze this region?
It would be the temperature change. That would be Q equals MC delta T.
That's right. What's the equation we would use when we're moving along this region? What's the equation that we use to analyze movements along this region of the graph?
That'd be Q is equal to positive or negative ML.
Good. If we're moving in this direction, is it positive or negative?
In which direction?
This direction. If we move in this direction, would Q be positive or negative? Ah, crap.
It would be positive.
That's right. With practice, that should be easier for us to see. Remember, what's the variable on the horizontal axis? What's the variable on the horizontal axis?
That'd be Q.
Yes. So when you're moving to the right, is Q increasing or decreasing?
It'd be increasing.
So that should make it clear that moving to the right would mean Q is positive. Suppose we were moving in this direction. Would Q be positive or negative?
It would be negative.
Right. With practice, it should be straightforward to read that off. Now, what would be the equation we would use when we're moving along this region of the graph?
It'd be positive.
What's the equation we use when we're moving along this region of the graph?
Q equals MC delta T.
That's right. But remember that for this equation, we don't need to decide ahead of time. Usually. Actually, sometimes you do need to decide if you're plugging in a positive Q or a negative Q. So that's true. But whether it would be positive or negative depends on which direction you're moving in. So the Q could be either positive or negative depending on what direction you're moving in. What's the equation we would use for analyzing this region of the graph?
Q equals plus or minus ML.
That's right. Let's say we're moving in this direction. Would Q be positive or negative?
It would still be Q equals plus or minus ML.
If we were moving in this direction, though, which would we choose, the positive or the negative sign?
The negative.
Yeah, then we would be releasing heat. Q is getting smaller. And if we're moving in this direction, would we choose the positive or the negative sign?
It would be, you would choose the positive one.
Because Q would be increasing. Okay. And what equation do we use to analyze movements along this region of the graph?
Q equals MC delta T.
That's right. So this graph really now organizes how we're going to do the problems. So notice that the equation here is the same as the equation here, but they're not really the same because remember that the specific heat for the solid phase can be different than the specific heat for the liquid phase. And that could be different than C for the gas phase. And these two equations look similar too, Q equals ML, but they're really different because here, what's the name of L for this region? What's the name of L that you would look up in the table here? What does L?
Could you repeat that?
What does L stand for in this equation for this region of the graph?
L stands for latent heat.
That's right. But what is it? We need to be more specific. There's a more specific name for it. How would you know what to look for in our table?
Oh, well, since like in that region, since it's, if you're going to the right, since it's melting, that's another name for a heat of fusion.
That's right. So here you would plug in the heat of fusion for L. Even if what you're really doing is freezing, you would still plug in the heat of fusion. What would you plug in for L over here from the table? what would be the name for this?
Heat of vaporization.
Yeah, even if you're really condensing, you would still plug in the heat of vaporization. So even though the equations all look the same, they have different constants. One thing I should have warned you about before is oftentimes I see students confusing a lot of these concepts. So for example, let me ask you, what's the symbol for heat?
That's Q.
What's the symbol for specific heat?
That's C.
Little c. What's the symbol for specific heat capacity?
That is also little c.
Right. Where, on the other hand, heat of transformation or heat of fusion would be called L. So the one mistake I see people make a lot is they confuse the heat and the specific heat. So I just wanted to warn you against that. Don't confuse the heat and the specific heat. What are the units for heat?
Joules.
But what are the units for specific heat or for specific heat capacity?
Joules per gram degree Celsius.
Yeah, all right. So, and remember, specific heat and specific heat capacity are two names for the same thing. All right. So let's see how this is tested. Can you read my writing here?
Yeah.
Okay, good. All right, tell me when you have that copied down.
Okay.
So let's do this together. So let's start by writing down a symbol for the question. What would be a good symbol for what this question is asking us?
Q.
Good. And let's get a prediction. What can you predict here?
50 grams of water steam at 110 degrees Celsius is cooled until it becomes liquid water at 80 degrees. Find the heat transfer. Well, since it's being condensed, that means that we have to remove heat. So that means since it's that means that Q is going to be a negative number.
That's a good prediction. We knew that as soon as we saw the word cooled. The way you're cooled is by losing heat. Now, where should I put a dot for my initial point?
Your initial would be at 110 degrees C in the gas phase.
That's right. That's what you always have to specify. You have to specify the temperature and the phase. So that was a good answer because you gave the temperature and the phase. So here we are at our initial point of 110 degrees in the gas phase. And where should I put a dot for the final point?
80 degrees C in the liquid phase.
I'll call that over here. Final 80 degrees. Now, how many processes then are going to take place? That might be kind of a weird question. How many kind of steps are we going to need to get to go from initial to final? That might seem like a weird question, but do you see you're going through 3 steps? You have to go through this portion of the graph, then this portion of the graph, then this portion of the graph. We could call that step 1, step 2, and step 3. Those are the 3 steps that we have to go through. So now we can start working this out. We can say the total Q is going to equal Q1 plus Q2 plus Q3. Now, what equation should we use for Q1?
Well, Q1, since it's going from steam to liquid, that would be a phase change. No, that would actually be, yeah, that would be a phase change. So we'd have to use Q is equal to plus or minus ml.
Now, I think there was a mistake there. Step 1 is this region of the graph, right? What's changing in this step 1? Is the phase changing or is the temperature changing?
Well, it's, oh, so, well, yeah, it's going from gas to liquid.
I think you're having some trouble reading the graph. So phase 1 is from here to here, right? I think the problem you're having is that you're not really breaking this up into 3 steps. Do you see the 3 steps I broke this up into? From here to here is step 1, from here to here is step 2, and from here to here is step 3. All I'm asking you so far about is step 1. So when we go from here to here, so what does this represent? What temperature does this point represent?
That'd be 100 degrees Celsius.
Try again. What temperature does this point represent?
Oh, number 1, that's 110.
And what phase does it represent?
The gas phase.
Now, what temperature does this point represent?
That would be 100 degrees in the gas phase.
That's right. So, in step 1, are we changing temperature or are we changing phase?
We're changing the temperature.
That's right. And what's the equation for analyzing changes in temperature?
Q equals MC delta T.
That's right. It didn't sound like that was the equation you were reaching for at first, but now we can see we need this temperature change formula. So I'll call it MC delta T. I'll call this C1. Maybe we should call this delta T1. All right. Now, how about for step 2? What should be the equation we're going to use to analyze step 2?
Could you repeat that?
What equation are we going to use to find Q2? What equation do we use to analyze step 2 from here to here?
Well, since step 2 is just it going from a gas to the liquid phase, that would be Q equals ml.
That's right. That's the phase change. But remember, this equation, we have to plug in the plus or the minus ourselves. So should it be plus ml or minus ml?
It'd be minus because it's going from a gas to a liquid.
Right. That's a point to really highlight because I think you can see how easy it would be to leave that out. If you put a plus sign here, all of our work will be wrong. So it's really important to remember that when we use this equation, we have to decide whether it's plus or minus. Now, how about for step 3? For step 3, what's the equation we're going to use?
Q equals MC delta T.
And now here, remember, there is no plus or minus, so we're just going to add that. The plus or minus will be taken care of by the formula itself. And I'm going to call this C3 and delta T3, because those are different than the ones over here. All right. What should we plug in for M?
So M is going to be 50 grams,
And then for C1.
2.01.
Good. So it's good that you use the specific heat here for solid water. Solid water is 2.01. And this is getting complicated, so I'm not going to plug in any units. Make our life easier by not plugging in the units. We just have to check that the units are consistent. How about for delta T1?
It would be 100. It would be fine. So it's initially at 110, then it goes to 100, so it'd be negative 10.
Okay, that was a good answer. Most people get that wrong, so that's good that you answered that correctly. So for step 1, the final point is here. The way a lot of people get that wrong is they would say the final temperature is 80. Well, that's the final temperature at the end of all the steps, but the temperature at the end of step 1 is 100. So in step 1, we're only losing 10 degrees. And it's good that you put in a negative sign for that. 100 minus 110 is negative 10. So that's good that you got that right. What do we plug in for M here?
M would be 50 grams.
Still. And for L?
Since it's going from the gas to a liquid, it's going to be condensing, so that would be the heat of, it'll be condensing, so it'll be the heat of vaporization of water, which is 2,260.
That's right. We need to use the heat of vaporization. It's not vaporizing, but we still use that even when it's condensing. So that's 2260. Good. What do we plug in for M here?
50 grams.
Still 50. And for C3?
4.184, since we're dealing with liquid water.
Yeah, let's make our life easier and just use 2 decimal places. 2 decimal places is good enough. 4.18. Now we're dealing with liquid water, so we can get that from one of our tables. Good. And then what about delta T3?
Negative 20.
Good. So again, sometimes people get that wrong because they think that they should do 80 versus 110. But now for step 3, we're just comparing 80 and 100. And it's good you said it was negative 20 because the temperature is decreasing. Notice how we had to put the negative sign in here, but notice that here the negative sign takes care of itself if we put in the temperature correctly. And here the negative sign takes care of itself if we put in the temperature correctly. All 3 of these terms are going to end up being negative because we're losing heat in each case. But for these equations, it comes out negative automatically if you put in the right if you calculate delta T correctly. Okay, now what?
Now we just do all the multiplication and add all the individual Q's.
Let's do that.
And I get a total Q of negative 118,189 joules.
Say that one more time.
189.
I'm sorry, can you say the whole answer again?
Negative 118,189 joules.
Okay, sounds good. I got 185. We probably rounded off a little bit differently. Joules. Good. And it matches our prediction. We were predicting it would come out negative. Notice that all 3 terms ended up being negative. This is kind of an unwieldy number, so it might be more sense to change this into kilojoules. How would you convert that into kilojoules?
Divide by 1,000.
So what would it be in kilojoules?
118.189.
So as a unit conversion, you would write that like this. And you write, it would still be negative. I might round that off to just negative 1118 kilojoules. So sometimes that can be convenient if this number comes out to be too big. Okay, so this is our first relatively difficult problem where we had a whole bunch of different steps here. Now you can start to see where the heating curve can be helpful. when you have these big multi-step problems, I think it's really important to use the heating curve to keep track of the different steps. So what beginning students sometimes try to do here is they try to do this in one fell swoop. But you can see we can't do this in one fell swoop because there's really three different steps. We have to analyze first a temperature change, then a phase change, then another temperature change. There's no way to just do this with one equation. So the key here is make sure, try to write things down just like I have them here. Try to write things down the way I've written it down. Always use a heating curve, label the initial and final points, and then identify all the different steps. And then you can lay out each of the steps here. That's the way to be organized and avoid making mistakes. And like I said, the mistake that people would be most likely to make here is forgetting this negative sign. So that would be one thing that it's especially important to highlight. Okay, good. I should have erased the old original and final points a long time ago. So tell me again, what does this point represent? How would you describe the substance at this point?
That is solid ice at 0 degrees Celsius.
Good. How about this point?
That'd be liquid water at 0 degrees Celsius.
Good. And here?
Liquid water at 100 degrees Celsius.
Good. And here?
Water vapor at 100 degrees Celsius.
That's right. I think one of the keys to getting these problems right is interpreting those points correctly. I think that was giving us a little trouble on the previous problem. All right. So let's try this problem. Talk me through how you would attack this.
Five grams of ice at negative 10 degrees Celsius is heated to liquid at 20 degrees Celsius. Find the heat transfer of the water. Well, we know that it's going from negative 10 to 20 degrees Celsius, and there's a phase change from ice to liquid water, so therefore we're looking for a positive Q.
That's good that you made a prediction.
So we have the mass and we have the change in temperatures. But since it's going from, first is going from ice from negative 10 to 0 degrees Celsius, so that would be the first step. Then the second step is going to be, it's going to raise the temperature from 0 degrees Celsius to 20 degrees Celsius and change it to water. So that'd be our second step. So in the first step, we would have to use Q equals mc delta T. But actually, no, in the second step, it's going from ice to water, and it's still staying like at 0 degrees Celsius. So here we'd have to use Q equals plus or minus ml, and in this case it'd be positive because we have to add heat in the second step. And then in the third step, it's going to be water, but it's going from 0 degrees Celsius to 20 degrees Celsius. So here we'd have to use Q equals mc delta T. So that means that in the first step, Q is equal to 5 grams times C for ice, which is 2.01, times delta T, which is final 0 minus initial, which is negative 10, so that's positive 10. The second one, Q is equal to positive 5 grams times L, which is, since it's going from ice to water, that means it's melting, so we use heat of fusion, which is 334 joules. And then 3, since we're using Q equals mc delta T, it'd be 5 grams times 4.184 for liquid water times the change in temperature, which is final 20 minus initial 0, which is negative 20. And then we just add all them up, so and I get a total of 1,352 joules.
Okay, so let's see. You figured out the question, you made a prediction. Now, at first here, it sounded like you thought there was only 2 steps, but then you caught your mistake. So it's good that you caught that mistake. There's really 3 separate steps. At first you were saying that the second step was melting the ice and changing it to 20 degrees. But you can't do both a temperature change and a phase change in one step. Remember that the main lesson from the heating curve is that at any point in time, you're either changing the temperature or you're changing the phase, but you don't do both of them simultaneously. We have to break this up into steps where only the temperature is changing or only the phase is changing, because otherwise we won't know what equation to use. So that's an important thing to have in your notes. In each step, you should be only changing the temperature or only changing the phase. That way you know which equation to use. You should never have a step where you're both changing temperature and changing phase, because then you wouldn't know what equation to use. So you caught that mistake and you fixed that. So that's good. Forget about the math. Forget about the math. In common sense terms, should Q1 be positive or negative?
Q1 should be positive
How do you know?
because you're going from -10 to 0 degrees Celsius.
That's right. Or even more clearly, it's just because we're moving to the right on the graph. What's the horizontal variable in this graph?
The horizontal variable is Q.
So what does it mean when you're moving to the right? What's happening to Q?
It's increasing. It's becoming
increasing.
greater, more
So
positive.
Q should be positive. So how about in step 2? According to the graph, should Q be positive or negative in step 2?
It should be negative. Oh no, in step 2 it should also be positive because we're going from ice to water.
That's right. So common sense, you would have to add heat to go from ice to water. But do you see, you can also just read that right off the graph. We're still moving to the right. As long as you're moving to the right, you're moving to a bigger Q. So Q should be positive. How about in step 3? Should Q be positive or negative?
It should be negative because you're going. Well, it's negative because
In common sense terms, in step 3, forget about the math for a second. In common sense terms, in step 3, should Q be positive or negative?
well, in common sense terms, it should be positive because you're gaining heat, but because of the math,
Right.
it
Well, let me help you with
turns out
that.
to be negative.
Okay. So that first answer you gave was correct. In common sense terms, we should be gaining heat here. You can see that in 2 ways. First of all, the temperature is going up. The only way for the temperature to go up is if you're gaining heat. And also, you can just see that mechanically from the graph. We're still moving to the right. So Q should be positive. So what did we just predict? Did we predict that Q for this term should be positive or negative?
Q should be positive.
In fact, I think we predicted that Q should be positive for all 3 terms, right?
Right.
All right. However, you actually got a negative Q here, right? For part 3, you got a negative Q.
Yes.
So we must have made a mistake down here. That doesn't make sense. This must be a mistake. So let's see where our technical mistake was. How do you calculate delta T3?
It's final minus. Oh, that's probably what I did wrong. It's final temperature 20 degrees minus initial, which is 0.
Final minus initial. And that comes out to be what?
418.4.
Oh, I'm sorry, what does the delta T come out to be?
Oh, positive 20.
Positive 20. So there was a technical math mistake there. But the thing I really want to emphasize is that we should be able to easily catch that mistake because it should be obvious from our graph that Q was positive here. It's obvious that we're still moving to the right, so it should be obvious that all of these terms should have come out to be positive. If any of the terms came out to be negative, they don't match our common sense. So that's a mistake we should have been able to catch, even if we made a careless error here. So that's something to watch out for. Do you see how the graph tells us that delta T, that Q should be positive here?
Yeah.
Because we're moving to the right, so that's a good way to catch your mistake. So if you really did final minus initial, that would be 20 minus 0 here, and that would come out to be positive 20. So let's figure out Q again.
So Q now is 2189.
So what's the answer?
2,189 joules.
Positive or negative?
Positive.
Right. But notice it's not just the total Q that has to be positive. The logic of the problem shows us that each of the individual Qs has to be positive too. That's how you can see that we'd made a mistake before. All right, so this is the correct answer. Okay, so let's see. We had, so your general process here was good. Once you saw that there was 2 separate steps, the problem you had was with the sign here. So that's something that we need to watch out for. Okay, so that would be a good example for you to go back and try again on your own. Oops, didn't want to do that. Let's do a little drill here. What is Q for this process? Positive or negative?
Positive.
Good. How about for this process?
Negative.
That's right. How about for this process?
Negative.
That's right. How about for this process?
Positive.
That's right. So it's oftentimes the case in science that the signs give people the most trouble. But even if you make a technical mistake, you should always be able to catch it by just using your common sense. You should be able to look at each term and ask, does this match common sense? We should be able to look at each term and just see whether we really expected it to come out positive or negative. Okay, now when you take your actual test, I'm not 100% confident that the tables you see are going to look just like this. When you take the test and they give you the heats of vaporization, they oftentimes will write the heats of vaporization or fusion like this. They might say that for water, say, it's 0.334 kilojoules per gram. You might see a table that's in kilojoules per gram. How would you interpret this number as the heat of vaporization for water? What would this tell us?
Well, for every 1 gram of water, it would require 0.334 kilojoules to raise to melt that water, that 1 gram of water.
Yeah, this was the heat of fusion, I should say, so it would take that much to melt that water. Good. But the problem is that the other table, the specific heat is pretty much always going to be in joules. Specific heat is almost always given in joules. But heat of fusion and heat of vaporization are often given in kilojoules. Well, that's a problem when we're doing a problem like the one that we were just working on. I just erased our work. But in the problem that we were just doing, we needed to use consistent units in all the terms. You can't be using joules in one part and kilojoules in the other. So the thing I'm trying to warn you about is if some of the units are in kilojoules, you have to change them into joules. You should change everything to be into joules, probably. So for example, let's say that you were given this number, 0.334 kilojoules. What calculation would you do to change this into joules per gram? How do you do a unit conversion to change this into joules per gram?
Just multiply it by 1,000.
Good. What's the unit conversion you're doing here? It's 1,000 what over what?
1,000 joules over 1 kilojoule.
Right. Then the kilojoules will cancel. And then you'll get what we already know is correct. And the reason you have to do this is now this will be consistent with the specific heats, which are also in joules. So that would be a good thing to put in your notes for the test. Hopefully they're going to use this table. This is a real nice table because everything is in joules. But it's actually very common for them. They might not even give you a table. On the test, they might just give you the constants inside the problem. And they might give you the heats of the latent heats in kilojoules per gram and the specific heat in regular joules. So if they do that, you have to change the kilojoules per gram into joules per gram. So it looks like you know how to do that. Was this one. Now notice this table looks a lot different. It still has some specific heats in joules. But notice now the units for the heat of fusion and vaporization looks very different. What are the units here for the heat of fusion?
The heat, everything's giving in kilojoules.
But there's a bigger problem. What are the units for heat of fusion here?
The heat of fusion is 6.01 kilojoules per mole.
Per mole. Do you see how that's different from the old table? The
Yeah,
old
that one was
table
in
was for
grams.
grams. I'm a little surprised. I don't know. Is this a table that your instructor gave you specifically, or
Yeah,
yeah?
both of them.
Okay. Now you sent me that you sent me a whole packet of practice problems, and in that packet, I don't think that you would ever. So basically, if the problem is in moles, this would be a good table to use, right? And if the problem is in grams, this would be a good table to use. All of the problems in that little packet you gave me were in grams. I didn't see any problems that were in moles. So as far as I could tell from that table, you'd want to be using from that packet, you'd want to be using that. That's a lot more common for chemistry. For chemistry, for these types of problems, you're usually going to use grams. But anyway, that's something to watch out for. Pay close attention to the units on any constants that you're given and make sure the units are appropriate. If you were given these in terms of moles, then you would have to change grams to moles. Probably the best thing there would be to change the grams to moles of the substance. But I don't think you actually had to do that for the practice problems you sent me. For the practice problems you sent me, you could just use these. So anyway, the lesson is watch out for the specific units in the constants that you're given and make sure you're using consistent units. Remember, I don't recommend writing down the units in your equations. If you write down the units in the equations, that just makes the algebra messier. But what I do recommend is before you write any numbers down, make sure your units are consistent. Make sure your units are consistent going in.